Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
First of all, good morning, and I'd like to thank the organizers for the opportunity to talk to you and the opportunity to tell you about the very first stages of forming stars and forming planets, and also to highlight some of the research that we do here in Michigan. And first, just I don't want to talk too much about planetary systems, just to point out a few features of them. And we have our planetary system that we all know. We have the rocky planets, and then what we call, that are mostly made, these rocky planets, of rocks, silicates, things like that. Then we have this region, we have like what we call the giant planets that have rocky cores, and then they have envelopes that are gas-rich, mostly hydrogen, helium, and other traces of other elements. And then outside we have Pluto and what we call Kuiper objects. But of course, this is only our planetary system. Right now, so far as there are like 340 planets, exoplanets discovered and counting. And this is information from the New York Times on Square Root Day, 339. That was Tuesday. And they are, they've been discovered all the time. This was until end of 2008. And I won't talk too much about exoplanets because this is a completely different talk. But what I want to point out to you is their properties. This plot shows like the 20 known multiplanetary systems. Many of these exoplanets now have multiple planets associated with them. And what I plotted here is just for each star, the distance from the star in which they have been found. That this is in units of astronomical units, the distance from Sun to Earth. And for comparison, I put our solar system here. And the size of the dot is an indication of the mass in Jupiter masses. So one Jupiter mass could be something like this. And this came out a little bit bigger because I couldn't shrink it as much. But what you see is the point that I want you to take from this is two things. That there is no regularity. In fact, you can find planets anywhere, and there is a very large range of masses. You can have multiple giant systems. They can be at very different distances from the star. So the main point is the very large diversity in planetary systems that we have discovered so far at least in our solar neighborhood. So when we are trying to understand how planets form, we have to understand two things: how they form, and also why are they so diverse? So why do we have so many different possibilities for them? They do have some common properties, and some of these common properties are that we always have in the system, the planetary system, the star is at the center. The star is at the center, and the other property is that most of the planets and most of other objects are always like in a sort of a disk, which is rotating around the star, right? So that's what we try to find out, to understand how to form. Okay, so then we go back in time and trying to understand how we form these systems. Well, just for perspective, our solar system is in our galaxy. This is, of course, not our galaxy, but our twin galaxy Andromeda. And the solar system is in a location like this. And the thing is that most star formation in the galaxy occurs along these regions that we call spiral arms in the galaxy. Spiral arms are regions of very high density of gas and dust. and they are better seen in the infrared. For instance, in here I compare I compare the optical image that I showed before with the image, the same image of the same, an image of the same object, but at infrared wavelengths. And you see that in there, the spiral arms are very clearly traced. And they are traced by the dust, because the dust is cold and emits at infrared radiation, and so it traces these arms and thus the star-forming regions. Now, just a little parenthesis, why is the dust cold? We know this is Saturday morning physics. You've seen that many times. Electromagnetic radiation has different wavelengths, comes in different flavors, from X-rays, gamma rays, X-rays, up to radio, from very small wavelengths to meter-sized wavelengths in the radio. But we only see the visual, right? This is the visual range, where we call the rainbow colors. The infrared is just longer wavelengths than the visual. Now, the other thing that I wanted to mention is blackbody emission. Most objects emit, in principle, like black bodies. Now, what's a black body? A black body emits all the energy that it absorbs. So it absorbs energy and emits all that energy, and it has a temperature, adjusts its temperature so it can emit and absorb and emit all the temperature. Now, the temperature of the black body decreases as it absorbs less energy. And the other property of a black body, it is that as it gets cooler, it emits at longer, most of its radiation at longer wavelengths. So in here, for instance, in this plot, I show like the emission of a black body as a function of wavelength, and I compare black bodies for different temperatures from 20,000 to 500 Kelvin. And what you see is like the 20,000 object, 20,000 K star, for instance, which would be a very blue star, will emit most of its radiation in the UV. Something like the sun that would be around 5,000 would emit in the visual, and then something as cold or colder than 500 would emit just in the infrared region. Now, this interstellar dust that is in these arms, it's heated. How is it heated? It's heated by absorbing radiation from stars that are very far away. So it absorbs little energy, and therefore is very, very cold. And it's so cold that the range of temperatures is usually between 10 and 100 Kelvin, which of course is really, really cold in Fahrenheit terms. Not even an Arbor got as cold in January. So it's bright in the infrared. So this is important because, of course, that's what we look at. Things that are, the dust is cold and dust is tracing the star-forming regions. Now, there is another problem. Both the UV and the infrared radiation is blocked by the Earth's atmosphere. So we have to observe it with telescopes that are in satellites outside Earth. And I show you here just the three great observatories, as they've been called: Chandra, that observes in X-rays, HST, that can go from the ultraviolet visual, and the near-infrared, and then the Spitzer space telescope that observes in the infrared, and that it was launched 5 years ago, and that has provided observations that have really revolutionized star formation, because it's really tracing those star-forming regions. And I'll be talking of some of those results of some of those observations. Now, coming back to the spiral arms. Spiral arm, when you see a spiral arm, it's actually patchy, it's not uniform. It's got these regions of high density. And these regions of high density is what we call molecular clouds. Now, even looking inside a molecular cloud, again, it's not uniform. It's got like clumps on it. And these clumps we call molecular cloud cores. And it's in this molecular cloud cores where stars form. Again, when we look at a typical galaxy, we will see like these regions, and those regions, like they are dark. These are regions of high dust, And the dust is actually making the image dark because it absorbs all the radiation, but it's tracing a region of star formation. I mean, and here it looks fuzzy because, of course, the galaxy is far away. A much closer region observed with a Hubble image would be something like that. But the point to see is that it's very, very dark. So one of these star-forming regions, one of the most observed star-forming regions, are the closest massive star-forming region is in the Orion Nebula. We all know that in the Orion constellation. And again, we see one portion of this nebula, and you see like a very dark, that's observations with HST, with the Space Telescope, with the Hubble, and then this is the same region but observed in the near infrared, again with NIGMOS, an instrument on HST. And what you see is that because the dust absorbs less in the infrared, we can see deeper, and then you see these star clusters that are actually hidden by the dust in the visible. Therefore, in fact, most of the youngest objects are hidden inside molecular clouds. This is the Barnard molecular cloud. You see it's completely dark, but when you see it in the infrared, you see like all the stars emerge, come out. And I just want to show you a couple of movies that are really amazing, but just to show you what we're going to see. This is like the initial and the final images of the movie I will show, but this is a globule inside the cluster Trumpet 37. There is a very hot star in here relative to the cluster, to that globule, and is illuminated. So you see it is this region of very high density, which is dark because it's got high gas and dust, a lot of dust in here. It's very dark, and the surface is actually shining in the visible because it's illuminated by the hot star in here. Now, when you look at it in the infrared, you see the opposite. The dust is actually shining, and you don't see this extra emission. Now, so I'll show you a movie which is actually nicer, which what we'll do is we'll go again from the optical to the infrared, and you'll see how the dust turns to dark to bright. See, it's just emerging. And this is already 24 microns, needs data. And in this next slide, this is another of these regions. I don't know if you can see with the lights, but inside this very dark region in here, it's not a hole, it's actually a region of very high density, a region of very high density here, of a lot of dust. And I want you to focus on this little object in here. This little object was known, this is a visible image, and it's an outflow. It's what we call a Herbig arrow object. It's actually material that is being ejected from the central star, very young star, that is shocking again interstellar medium and producing this emission. So we're going to see how this opens up as we go into the infrared. So we approach it, and again, focus on this little object, and you'll see what happens. You see that the outflow, all that outflow begins to emerge, right? So because we go into very long wavelengths, and we could see inside the dust and inside the star-forming regions. Now, coming back to the molecular cloud cores, just to see how stars really form, we have these cores, and because they are so dense, they absorb the surface, absorbs all the radiation, so the interior of the core is very, very cool. So that means that the core, you cannot build enough pressure to counteract gravity, and then the core is collapsing. But the cores are rotating. Everything in the universe is rotating, so it has some angular momentum. And when it collapses, it has to conserve angular momentum. So as a result, when the core actually collapses, it forms a disk. When it collapses from distances of 20,000 AUs to 100 AUs, it actually forms, all the matter is in a disk. So why a disk? Well, suppose that you have a collapse that something was originally spherical, right? So at some point, particles of matter that is coming from opposite regions in the original sphere get to the equatorial plane, and then in the equatorial plane they collapse, they choke with each other. What happens then is that the vertical component of the velocity actually dissipates in this shock, and what remains is like the rotational velocity. So everything will then stay after some rearrangement to conserve angular momentum here. Everything will remain in the equatorial plane. So naturally, the natural consequence of the collapse of something spherical but that has some angular momentum is that everything will end up in a disk. So that's what you expect, just because of conservation of angular momentum. And do we observe these disks? Yes, we do. These are images from HST and of very early objects. They are protostars. They are still actively accreting mass from their disks and their envelopes. And the disks are these dark lanes in here. Those are the disks. And all this extra stuff above and below is matter from the envelope that is actually falling onto the disk. And I'll show you other images of disks in later stages. Again, this is the Orion constellation. You can see like the Orion belt. This is like the Orion Nebula cluster, like the 4 stars of the Orion giant. And then we are focusing now on the nebula. This is a portion of the nebula, the center of the nebula. And we're going to focus even more on the objects, some objects that have been discovered in there. These objects are actually stars surrounded by disks. And we can see them, like in here, in silhouette. That is, the disk is in front of the bright background, and what you see is just the disk hiding the background. These are the silhouettes. And then we have, like here, these are the silhouette disks, and there are many of them. And then we have this other variety, which is very interesting too. The little disk is in here. But what happens is that it's very close to a hot star. And the hot star is actually heating up the surface layers of the disk, and it's evaporating very quickly. And then interacts with the radiation and the winds from the hot stars and forms this sort of tear-formed objects. And those are called proplyds. So these were among the first direct evidence in the optical direct images of disks in the Orion Nebula cluster. Then there are obviously other images like HH30, and HH30 is also very interesting. Again, the disk itself, we are seeing it sideways, right? Edge on. So the disk is actually just this dark lane here. So the radiation from the star bounces on the surface of the disk and then comes towards us. And so it has these two bright patches above and below. But the interesting thing about this object, because again it's very young, is matter is falling inside towards the star, but some of that matter is actually ejected in its outflow. And the outflow is very variable, as you can see. This is a combination of pictures taken a year apart, and you can see how variable it is, this ejection, right? So this, again, is a very early object. More evolved objects, the jets are not so conspicuous, we don't see them. And I just wanted to show you this image that was discovered by a collaborator of us like two weeks ago. And we are working on it, trying to interpret it. But how violent and changing these phenomena are. These pictures were taken 4 days apart, and you can see how the brightness of the surface changes just in 4 days. We're still trying to understand why that happens. Again, but besides images, the way that we study disks is by looking at what we call spectral energy distribution, which is like how much energy it emits at different wavelengths. And what I show in here is like the emission that you expect. This could be the infrared range. That is the tail of the black body of the star. What we see in here is the star, and this could be just the emission of the star by itself, right? Just the tail of the black body distribution. Now, suppose that the star is surrounded by a disk. Then what happens is that this disk is heated mostly by the star, and therefore what happens is that the temperature decreases with distance to the star, because each annulus is farther and farther away from the star, so it's going to be cooler. And so what happens is that each annulus of this disk will emit a longer and longer wavelength. And as a result, the emission from the disk would be this excess above the intrinsic star and extending to longer and longer wavelengths. So this is what we look for, and this is what we study from these disks. And studying this spectral energy distribution from this, we have inferred a lot of properties. This is like a SSE picture of a full disk, as we call. So we now know that these disks are mostly, these primordial disks, the original ones, are mostly gas, and thus is around like 1% of the total matter, just like and they are circling around the star. And the mass is like, the mass of the disk is around less than 5% of the mass of the star. So typically you have like 10 to 50 Jupiter masses in those disks. So you have plenty to make a planet, a giant planet, or several. The velocity is Keplerian, just like in the solar system. That means that the innermost rings are rotating much faster than the outer rings. One important thing is that disks are changing with time. Why are they changing? For two reasons. Why is because the mass of this disk is actually being accreted onto the star, and I'll talk about that. And the other reason why they're changing is because these dust particles that are in there are actually colliding with each other, growing, settling towards the midplane. So one important thing is then that disks evolve. They are not stationary. Now going back to the question of this accreting mass onto the star. We have, as I said, Keplerian rotation, so the inner parts of the disk are rotating faster than the outer regions. So this differential rotation causes rubbing between adjacent annuli, right? So this rubbing transfers angular momentum outside, because the faster inner rings try to push forward like the outer rings, right? Make them go faster, and therefore there is a net transfer of angular momentum outside. But then the inner rings that had lost angular momentum because they become slower, they've been braked by the rubbing with the outer rings, they actually fall inwards, right? And the result is that you have matter actually spirals into the central star, and it's finally accreted onto the star. At the same time, of course, the outer regions of the disk expand to conserve angular momentum. So as a result of this process, this is an accretion disk, what it's called. As a result of this process, with time, the mass of the disk will decrease, and it go part onto the star and maybe into planets, as we will see. But the mass is changing. Now, the other thing is what's happening to the dust. What we call dust is like little particles that are less than 1 micron size. And they start with these sizes, a little bit, it's submicron actually, what we have in the interstellar medium. And then in the disk, what's going to happen is they start colliding with each other, and then some of them stick together and they grow with time, right? And the process, as we see that, this is of course a very simplistic example, is that the dust originally was very small and was all over the disk, right, mixed with the gas. But then it starts colliding, starts growing, and then the particles, the larger particles, start falling towards, sinking towards the midplane of the disk because of their own gravity. And then in the midplane, you have further grain growth, further collisions, further grain growth, and eventually you get to a situation in which you form planetesimals, objects that are meter to even kilometer size objects, but they are all forming in the midplane. Now, what type of materials do we have? Well, the type of materials that we can form this way in the disk depends on the temperature, on the local temperature. Because, for instance, iron and nickel metals, they do not evaporize, sublimate until temperatures that are 1600 K. Now, silicates, the rocks, they actually start vaporizing above 1300 K. Now, ices, on the other hand, which is the ones that are important because these are the ones that can hold hydrogen in here, water, methane, ammonia, these require temperatures below 150 K. Above that, they will just evaporate, right? So that this differentiation that metals, rocks survive to high temperatures while ices can exist just at low temperatures mean that this differentiation means that we expect to see different materials in the planetesimals that are being forming in the disk. The inner region will be mostly rocks, while outside that you can have ices and other essentially hydrogen compounds. And that naturally explains, at least a first approximation, why in the solar system we see rocky planets inside and then the giant planets outside. These have these envelopes of hydrogen and helium, which inside this region, which we call the snow line, which is the region above, inside which the temperature will be high enough that would evaporate, we can only have rocky planets. Now, let's take a closer look to what we think a giant planet forms. This is an image of what we think Jupiter is made. And Jupiter has a planetesimal core made, again planetesimal, made of rocks, silicates, things like that. And then it's surrounded by this very large envelope of rich in hydrogen and helium. Now, the model that, the most accepted model for planet formation is the following. In here, what I show is like the growing mass of the planet as a function of time. The idea is that because of these collisions between planetesimals, you start forming a core. The core of the planet begins to form. At some point, when it reaches some critical mass, then it starts accreting, it has enough gravity to start accreting a gas. And there is a period of very slow accretion of gas around this, the core, the planetesimal core, until like the mass of the core and the mass of the gas accreted are comparable. And after that, it follows a period of very rapid accretion of gas. This is called runaway accretion. And it's in this portion, this period in here, where most of the mass of the giant planet is formed. Right, so the time scales for this process are of the order of 10 million years or less, and of course it depends on the condition, the local condition of the disk, etc. But that's the way we think they form. An interesting thing is, of course, that again everything has angular momentum. So when we build matter is being accreted from the disk onto the core. And each planet is formed with its own miniature disk. And in this disk, we think is where the biggest moons of the planets are formed. Now, the other thing is that this process of accretion, first slow and then a rapid accretion, runaway accretion, can happen depending on the circumstances in several spots in the disk. So you could even have like multiple formation of multiple giant planets in a given disk. Now, the question we ask, when do planets form, these giant planets form? And we all know then, because of this process that I just explained to you, we need gas to make the planet, right? So, but we know that this gas is being accreted onto the star, right? So eventually the disk is going to run out of gas because we will expect it will go into the star. So the point is that we have to make the planet before the disk runs out of gas. So the question that we ask is, how long does the gas last in the disk? That's the main question that we investigate. So this is just a study by a postdoc that was here until last week. He just left, went back home. The idea was like look at different associations, stellar associations with different ages, right? And then look at the disk, find the disks in these different groups that have different ages. And how do you find the disk? Because you see this excess emission in the Spitzer bands that I mentioned you before. And that's what he did here. These are objects of different clusters and associations between 1 and 10 million years. And what you see is this rapid decrease of this frequency with age. Essentially, the gas in the disk or disks are gone by 10 million years. So that set a very upper limit, very strong upper limit to the time in which planets can form. Giant planets form during the first 10 million years of the life of the star. So the sun has been there 500 million years, but all the giant planets, Jupiter, they were formed during the first 10 million years. That's the first thing that we learn. Now, how exactly do we form the planets? Well, the idea here is these are results of hydrodynamical simulations by Frédéric Massé. And I'll show you some movies, but just to indicate to you what you're going to see. You see like the planet forming in here. This planet actually is accreting mass from the disk and drives these density waves, regions of high density, into the disk nearby. These waves carry angular momentum in the sense that the outer regions in here get angular momentum from the forming planet, and the inner disk actually transfer momentum to the inner planet. And when it does that, as this outer disk gains angular momentum, this edge of the disk gets angular momentum from the planet, it actually recedes. So, and the opposite happens in the inner disk, so you go and open a planet. So that's where we think are the first stages of the formation of a planetary system. Now, I'll show you now again the very first stages, and when the planet in these simulations I'll show you is still low. So the disk actually, what's going to happen, as you will see, is that the planet forms and is interacting with the disk. Right? Go ahead. Okay, here we go. So you see what happens is that the disk, which as it accretes, is actually pushing the planet inward. The planet is migrating inwards. And because of the planet mass is not so low, it just can go inwards, and it has the danger that the planet actually fall into the star. So planets of very low mass, if they don't have enough mass, they eventually can form, but they actually be pushed into the star and be eaten by the star, say, disappear. Now, other things may happen, right? It may happen that if the mass of the planet, like in this case, the planet can actually, as it migrates, it can accrete enough mass from the disk then it can actually, but by interaction with this density wave interaction, exchange enough angular momentum with the disk that it can actually open a gap. So as you see, it all depends in properties of the disk, in the sense that how much does the planet accrete from the disk, which will depend on how is the surrounding disk, where it is located. So there are many conditions that can lead to different outcomes, right? So, in this case in particular, the planet opened a gap and stayed there, and migration stopped, and the planet did not end in the disk. So essentially, the type of evolution that we expect is something like that then. Okay, we start with a full disk, planet starts to form, gap starts forming, the inner disk will eventually disappear, going to the star, and what we will end up is with a system that has the star in the center, a disk, well, it has a very large hole at the center, okay? Now, the question is, do we detect these holes? I showed you before the spectral energy distributions. That's what we would have from a star alone, and this is the type of spectral energy distribution that we would get from a disk, a full disk. Now, what would happen? That would be the full disk. What would happen if we actually had that hole in the inner regions of the disk, right? What would happen is that the hotter regions in the disk would be gone, right? Because those are the ones that will be closer to the star. And if they are gone, they're not emitting. So we will have the spectrum, the distribution of energy that will be emitted will be essentially like the star, and then it will go up because it will be like this outer region emitting in here. So we will have this spectral energy distribution showing like this dip relative to the emission of a full disk. And that would actually tell us that we are seeing these regions in the inner disk that have been already emptied out by planets. And exactly that's what we see in our Spitzer images. This comes from a press release from the Spitzer Space Telescope featuring one object like that we discovered in a group. More intriguing, though, is a gap, right? Because a gap, that's even an earlier phase, right? How would it look? How would the spectral energy distribution look like? Well, again, this could be like the single star, this could be like the full disk, and that would be the spectral energy distribution of when you empty out the innermost regions. Essentially, you would have nothing here, just the star. But if you had a gap, right? If you had a gap, you still would have some remnant inner regions here, hot regions, right? Because the gap would be just between one another, but you still have some inner disk left here. So what will happen is that you will have emission like a full disk, very close to the star that is in the near infrared, and very far from the star in the far infrared, and you will have this hole in here in the spectral energy distribution that would actually correspond a hole in the disk, a gap, right? So this is a very exciting discoveries that we had here just last year. This is research by Caterina Spagliata, a student of mine, and she's graduating soon. But essentially, these are real data. Again, this is the star, and that's the radiation that you would expect from a full disk, the green line. And what you see is, again, that a long wavelength and a short wavelength, it emits a full disk, but then in between there is less emission, right? And we think that this is essentially that's due to the presence of a gap in this. That is the very first stages of planet formation. So what we think now is that we have identified these three stages in planet formation: the full disk, then the disk with gaps due to planets that are already opening the gap, and then these later stages in which the planet has intrinsically opened already these holes in the disks. Now, formation of terrestrial planets. I've talked so far just of the of giant planets. Well, essentially, after the gas is gone, and then you can safely form the planets with lower masses without danger of them being dumped into the stars by the gas. Then what happens is that collisions between left behind planetesimals can actually build up terrestrial planets. And of course, there is a lot of research on that, but that's the essence of the mechanism. And this can last much longer, can last 100 million years, depends on the models, depends on what type of disk you have. But essentially, they can form later on. Now, we still have to explain the diversity. Well, coming back to the diversity. For one thing, in the giant planets, as you saw, it depends how fast the matter can be accreted into the planet, and that will depend on the local conditions, for instance. But also, of course, it depends on how these planetesimals actually collide with each other and make the planetesimal cores grow. And of course, you can have like chaotic random motions, and then it can result in very different final conditions depending of just small changes in initial initial conditions. And I want to point out to you research done here by Althea Moorhead and Fred Adams, our host, and what they did in here, and correct me if I'm wrong, Fred, but I was in the committee, right? So the idea here is like they actually did many realizations, many models of planet interaction, planet migrating, and with different properties in the initial conditions and properties in the disk. And what they found is by doing that, of course, these initial conditions were consistent with what we expect of the possibilities that we expect from this. And what they found is that they could explain the observed range of properties of exoplanets with just by doing that, right? So in here, for instance, this is like the distribution predicted by some range of models compared to the observations, and you can see that there is a very good overlap. So the diversity is naturally explained just by changes of initial condition, and including these properties of some randomness in the distribution of what's happening in the mechanisms affecting the dust. Okay, so I am about to finish, but I'll just a quick summary of planet formation. We start with a cold core in a molecular cloud that is collapsing until its own gravity. Then a protostar with a disk and an outflow, it's formed. The outflow finally gets rid of the envelope, or you run out of mass, and then what's remaining is a disk. In the disk is actually accreting mass onto the star, and actually onto planets that may be forming in there after enough planetesimals have formed these planetesimal cores. Eventually, that opens gaps in the disk that make these big holes, so the planets may form, and this is like the expected sequence. And just for fun, the so-called planet discovered here by us last year is featured in the Scientific American top 10 exoplanets, the youngest planet. It's just amazing. So I just want to show you to end this simulation, which is really nice, and which is like a sort of a summary of the formation of planets in this. Again, those are hydrodynamical simulations. Okay, there we go. Again, we're seeing this has already formed a planet. And this planet has these density waves, and it's accreting mass from the disk. We're going to see it now sideways. Go far away, you will see. See it from different perspectives. We're going flat. This hole in here is actually boundary condition. You cannot go to the star in this simulation, so this is not realistic. Now we're going to zoom in into the star, into the planet, the forming planet. You're seeing it sideways. And we're going to see the disk that is forming around the planet. Because again, angular momentum, you form the planet surrounded by a disk. So the planet has its own disks, where again, by similar mechanism, the moons can form. We're going zooming in into the planets. We're going to see just the top of the planet, the upper layers, because of this hot planet, because of course matter is being accreted from in the equator. So this is the accreting planet here, the hot accreting planet. That's from below. Again, the disk around the planet. We're zooming out again. And there goes the disk. Goodbye. And thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.